Hello, this is Dr. Viv. I will now be talking about the opposite problem. Previously, we had considered differentiating under the integral sign with respect to some parameter in the integrand. Well, now I'll consider the opposite thing, which is to integrate under the integral sign with respect to a certain parameter. You can think of this as two sides of the same coin. So suppose I have an integral I which depends on some parameter lambda. And just to keep things simple, I made it a definite integral from a to b of some function which depends on not only the x parameter but also lambda dx. Now in applications, if lambda is not present, we have to manufacture it through a change of variables. I'll illustrate it with an example. Then the theorem of integrating under the integral sign says that if you integrate this integral here, I, as a function of lambda, with respect to the variable lambda itself, between some other limits alpha and beta, then the resulting double integral that you have with respect to both lambda and x, you can interchange the order of x and lambda. That's the content of this theorem. It's a very useful way of evaluating certain integrals, such as the famous integral in mathematical physics known as the Euler Poisson integral. And the Euler Poisson integral has got applications in almost every branch of engineering, physics, and every other subject, including mathematics itself. So the Euler Poisson integral is the following integral I, which is the integral from 0 to infinity of e to the minus x squared dx. Now, if you try to evaluate this through any normal technique of integration, you'll utterly fail. But this can be dealt with in many ways. There are many ways of evaluating this, and throughout this course we'll find additional methods. But this is one of the first methods that you'll look at. Now, from a graphical perspective, what does it represent? If you plot e to the minus x squared for positive and negative values of x, it is what's called the bell curve, or the Gaussian distribution, or the Gaussian function. There's got many names because it's so important. It goes off to infinity in both directions for both positive and negative values of x. It goes off to infinity, and then the maximum value of it is e to the negative 0, which is e to the 0, and that's equal to 1. So at 0 it attains its maximum value. So it looks like the bell curve. Now what we are trying to do is find the area from 0 to infinity, so we are finding half the bell curve's area. When we evaluate the Euler Poisson integral, we will have found half the area, so the full area can be found by doubling it. So the first thing is to manufacture this parameter lambda. How do we do that? Let's try to make a change of variables x equals lambda t, and if you do that, then dx equals lambda dt. The limits will remain unchanged because lambda is supposed to be a real number. So when x equals 0, the t parameter also is equal to 0, and so on. Let's try to now write our integral, which I initially wrote as I, is now a function of lambda. So that's going to be, I'll pull out this lambda. If I substitute for dx, I'm going to get lambda dt, so I'll pull the lambda out. So I'll get lambda integral 0 to infinity e to the minus, when I do x squared, I'm going to get lambda squared t squared. Okay, now it's all ripe and ready to be applied. Now what I'm going to do is I'm going to further integrate the left-hand side from alpha to beta. Okay, but before I do that, I'm going to multiply both sides by e to the minus lambda squared d lambda. So the procedure, what I'm going to do is multiply first both sides by e to the minus lambda squared d lambda, and then I'll set alpha equal to 0 and beta equal to infinity, from those two values there, and integrate. Okay, we're going to do that. So let me show you that. I, which is I of lambda, and I'm going to multiply it by the integral e to the minus lambda squared d lambda. Now if you think about it, there's no real difference between e to the minus lambda squared d lambda and e to the minus x squared dx. I'm just replacing the dummy index x by another dummy index lambda. So this is in fact equal to I squared. Well, that is also equal to the integral from 0 to infinity. So I'll be multiplying the right hand side by this and integrating it from 0 to infinity also. I've so far just done the left hand side. Now I'm going to do the right hand side. So that's e to the minus lambda squared times, there's already a lambda on the right hand side. So I'll get lambda, d lambda, and then there's of course this. So integral 0 to infinity e to the minus lambda squared t squared dt. So all I've done is taken this, multiplied it by e to the minus lambda squared d lambda, and further integrated with respect to lambda from 0 to infinity. The left hand side is equal to I squared and the right hand side is equal to whatever you see here. Now this is where I'm going to use a theorem. I'm going to interchange the lambda and the t integrals. So applying the theorem, I'm going to get the integral from 0 to infinity dt, and then I'll club everything else in the lambda integral. Now you notice that there's a e to the minus lambda squared here, and there's a e to the minus lambda squared t squared there, so the two can combine, and I get e to the minus 1 plus t squared times lambda squared. And then there's also this lambda, d lambda. So at this point, you can really see what's going on. Previously, you could not do this integral because you could not have used a u substitution. If you try to use a u substitution, if you write u equals x squared, you're going to get 2x dx equals du, and you don't have a 2x out there, but now you do. So a u substitution will really do the trick at this point. So let's start that u substitution next. So I'm going to take u equals 1 plus t squared times lambda squared. Now you see that that make this numerator u. So the exponent, it will make e to the minus u. So du will be, if I differentiate with respect to lambda, I'm going to get 2 lambda. Well, this is just a constant, so that stays 1 plus t squared times d lambda. But what I have here is a lambda times d lambda, so I'll solve for that. So lambda d lambda is equal to 1 upon 2 times 1 plus t squared just du. Now what about the limits? When u equal to 0, when lambda equal to 0, u will also be equal to 0. When lambda goes to infinity, u will also go to infinity. So the limits will remain quite unchanged. So the integral, I have I squared, which is that, and I'm going to rewrite this. The first integral will still be from 0 to infinity dt. That has not changed. But the inner integral, I'm going to now write in terms of the u variable. So that's going to be integral 0 to infinity e to the minus u. And for lambda d lambda, I'm going to write du divided by 2 times 1 plus t squared. Now 2 times 1 plus t squared is a constant as far as this integral is concerned, but not as far as that integral is concerned. So I can pull it outside and I'll get e to the minus u. Well, that's easy to integrate. So let's do that next. The integral of e to the minus u du is just negative e to the minus u. And this has to be evaluated between the limits u equal to 0 and u equal to infinity. Well, that's also not very hard to do. So that's integral 0 to infinity. Let me just take this half outside. So I get dt over 1 plus t squared. Now the exponential at infinity minus infinity becomes 0. So that the upper limit is 0 and the lower limit is going to be 1. But the lower limit is has got a minus sign So that's minus of minus 1. In other words, the whole thing is just 1. So I have here I squared equal to half times the integral of 0 to infinity dt over 1 plus t squared. The integral of dt over 1 plus t squared is just tan inverse t from 0 to infinity. Well, this can be solved. Tan inverse infinity is pi over 2 and tan inverse 0 is 0. So I've evaluated the famous Euler Poisson integral. Well, actually I've evaluated the square of it. The integral itself is got by taking the square root. Now, by the way, the area under the bell curve, the complete bell curve area is going to be 2i, and that's going to be the square root of pi, because I'm just doubling that value. So we have solved this problem. By the way, there is an alternative way of finding the Euler Poisson integral. Actually, that alternative way of finding the integral is actually done for the entire bell curve. So I want to just touch upon that also, just for your reference, and because that is an additional way of solving this problem, and the two ways are kind of related, and I want you to examine them and ponder about what the relationship might be. It's a little bit like the integration under the integral sign, except the two variables we have in the next method are on equal footing. So here's the next way of doing it, the second way of doing it, and that is, I'm going to call this I prime because it goes from minus infinity to infinity. We're going to evaluate the complete area under the bell curve. In other words, twice the Euler Poisson integral. Well, I'm going to change the variables to y. So in a sense, that bears the same resemblance as changing things to lambda, okay? So that's kind of like that. And then I'm going to do the same process of multiplying the two together, except when I multiply these two together, I'm going to get e to the minus x squared plus y squared dx dy. Now this is an integral over the entire xy plane, so you can think of this as a exponential bump in both directions. It's like a mountain or a hillock extending off to 0 in all directions. So this can be evaluated in polar coordinates. So I'm going to choose the substitution x equals r cosine theta, y equals r sine theta. Then x squared plus y squared will end up being r squared, and dx dy in polar coordinates, you can show that dx dy is equal to r dr d theta. Now, for those who are interested in showing this, all you have to do is take the differentials dx. I'll just indicate a little bit of what you need to do. Dx is going to be dr cosine theta minus r sine theta d theta, and dy is going to be dr cosine theta plus r cosine theta. Let me see, I have dr sine theta here plus r cosine theta d theta, and then you just multiply the two of them, and the cross terms will cancel out, and you'll get this. Okay, just try it, you will get it. Now if you do that, then I can get the following result. Remember, in polar coordinates, r goes from 0 to infinity and theta goes from 0 to 2 pi. So I prime squared equals integral from 0 to 2 pi on the d theta variable, and integral from 0 to infinity r dr e to the minus r squared. Now you're back to the same kind of trickery here, getting that lambda d lambda r dr and e to the minus r squared, simpler. Now I'll use the u substitution, u equals r squared, so du is going to be 2r dr. So I'll pull out the, I'll arrange for a 2 to appear here by multiplying and dividing by a half. So that'll exactly be the u substitution. So I get 1/2. The integral from 0 to 2 pi of d theta is just 2 pi. And then when I do this integral, I'm going to get minus e to the minus u from 0 to infinity. So that's again just positive 1 by the same reasoning as that one. So that I get pi. And so I prime is the square root of pi. So that is the complete area under the bell curve by a completely different method, although it's related to the earlier method.